Good morning, everyone. It really is a thrill to see you all here, despite the apocalyptic weather, the snowpocalypse as they call it. I'm thrilled to see everyone here. And I was thinking, what does it take to get high school students who have been listening to lectures all week to come out on their free day and listen to another lecture? So I don't know why you're here. But as I was thinking about that, I figured it's probably curiosity. Curiosity is a powerful thing. You're probably here to maybe learn a little more about the universe we live in. And curiosity played an important role as I was growing up. You could say that I was a curious child, in more ways than one. I love taking things apart, especially electronics equipment. I love taking apart DVD players, microwave ovens, you name it. And I think what I wanted to find out was how the function of the device could be explained. Different devices could be explained in terms of a picture involving the components, the resistors, capacitors, transistors, which are represented in a more fundamental picture of the workings, right? And so I became familiar with these different components and their different properties and tried to figure out how you would go about building a certain device. As I got older, and now in the research I find myself in today, it turns out I'm not really doing anything different. I'm asking the same sort of questions, now joined by physicists around the world, thousands of physicists around the world who just have a little more money, but are basically asking the same childish questions. What is the universe made of? How does nature work at the most fundamental scale? These questions are what we'll talk about in what I see as one of the greatest monuments of creativity, the story of particle physics, and how physicists conspire together to build the world's largest machine, really. So, let's talk about this question, what is everything made of? We know you're all very smart already in terms of this question. You know everything is made of molecules. Those molecules are made of atoms. That already is a fascinating idea, to think that the whole diversity of the physical realm, the moon, box of Cheerios, are all basically made of the same thing, molecules. And there are very many molecules, but they all share in having the same basic building block, which is an atom, right? Now, when scientists first thought about the atom, they knew there were these electric charges, which gave the properties of the different elements, but they were maybe just kind of clumped together, kind of a positively charged mush. So they didn't know. They weren't able to find out that structure until later, as they kind of shot bullets at atoms, tiny little bullets called alpha particles. They discovered that there was a structure underneath that all the positive charge was clumped into this pinpoint in the center called the nucleus, and the electrons represented this really spacious cloud outside of that. And now we come to the picture that all the high school students will tell us about, where the nucleus is seen to contain smaller particles called protons and neutrons. So again, you see this order just getting more and more complex as we look smaller and smaller. Protons and neutrons, you're probably all familiar with, but I want you to ask yourself a question. Protons, as you know, are positively charged, right? The neutrons, they don't really do anything. They're neutral. They're neutral, right? So there's no charge. So how do the protons stick together in the nucleus? What's keeping them together as they repel each other? If you do a quick calculation with Coulomb's law, you can see that there's at least 60 newtons of force exerted on the protons in a very small atom. So that's kind of like the weight of 6 kilograms, which is these protons are feeling. So a tremendous amount of strain at the heart of every atom. Maybe some of our younger audience members actually know, what is it that keeps those protons from flying apart? Somebody know? The strong force. Excellent. So physicists thought to themselves, there must be something overwhelming the electrical repulsion, some new force, and they're very good at giving things names, so they called it the strong force. In this picture, which is the current picture we have of the atom, the protons and neutrons were seen to be subdividable into even smaller particles known as quarks. Specifically, two types of quarks, up quarks and down quarks. What made the proton and neutron separate from one another is that the proton was made of 2 up quarks and 1 down quark. And the neutron was made of 2 down quarks and 1 up quark. And maybe someone later will want to ask me why I put them here with 3 different colors. That's an interesting property. And the springs here that you see represent the force field that I talked about, that strong force, and they are called gluons. So let's just wrap this up. We introduced these 3 particles. We already knew about the electron, but now we also heard about the up quark, the down quark, and now that horrendous table that you learned in chemistry class can really be boiled down to 3 little bits, and these do represent the 3 ingredients of all the atoms in the entire universe. With a few caveats, but as much as you can think of it that way. It's kind of like those cake mixes, right? Just add eggs and water, and there you go. It's very simple. Even you can memorize this. So you might be thinking to yourself, how do we know we've reached the bottom of this description? How do we know quarks can't be split into smaller pieces? And the answer to that is we don't know, although physicists have many theories, and there are good reasons to think that we have reached the bottom. But some theories, like string theory, for instance, postulate that there's still structure underneath that. What is known is that if we wanted to study these questions, if we wanted to try and split a quark, we would need loads and loads of energy, right, to shear those forces. And that's why physicists built a very, very powerful machine called the Large Hadron Collider. I have a hard time even beginning to describe this machine because it's really, really big. It's insane. This is a 27-kilometer proton demolition racetrack. Okay, so they probably said something a little more sophisticated in the funding review, but this is essentially what it does. It's a particle demolition racetrack, and it's 27 kilometers long in circumference, nestled under the very peaceful countryside of Switzerland and France. But under the ground, 100 meters under the ground, I'll tell you, it's not so peaceful for these protons. They are whipping around at 99.99999% the speed of light. And so yeah, they are not so peaceful. Okay, so they whip around like this, and if this is a racetrack, if the protons are going around this racetrack, you can think of it as having 2 lanes. It's two-way traffic. The lanes are separated. And to give you a sense again of that speed, the individual proton, there are many of them going around in kind of herds, bunches we call them, they have the kinetic energy equivalent of a housefly. So an individual proton, right, just an astounding amount of energy. Another way to think of it is they complete a lap. You know, they do over 11,000 laps per second as they go around this machine. How do you get them that fast? Electric fields. So particles are accelerated if they have a charge. They're accelerated in an electric field. So there are 16 of these different, what they call radio frequency cavities. They're basically boost strips, which are positioned around the ring. And every time the protons enter these cavities, they get a whopping kick. Now, as they get faster and faster, we need to really, it's like those, what's that Olympic sport where you hold this ball and you have, what's it called? Hammer? Hammer throw or something? Yeah, the hammer throw. Yeah, so you need to apply that centripetal force to keep the protons from swinging out. And that is done with magnetic fields. So they don't speed them up, they change their direction. They try to bend them inwards. And really, engineers tried their best to build the strongest magnets they could to contain these protons in a circle. And the best they could do was to contain them in a 27-kilometer circle. So if they could, they would have made the LHC smaller. But this, given the speed that we want, is how big the machine needs to be. So here again, you see the 2 little holes, which are for both lanes, right? One going in, one coming out. Now, if the LHC is a racetrack, if it has 2 lanes, it also has 4 intersections. And there are no traffic lights. So bad things happen to the protons. As they cross paths with each other, this 2-lane traffic, now they cross each other, and for a moment, they intersect. And you can see that up to 4 different circles here. Those are the locations. Now, I'm really abusing this racetrack analogy, but I think it will help you to think of the protons as cars, and now the particle physicists are the police, right? Police, okay, this is really stupid, but police are interested with laws, and particle physicists are also interested with laws. They're concerned with the laws of nature. And so they have installed traffic cameras on the intersections. That's the 4 things you see here. They're very big traffic cameras. They were called particle detectors. I don't want to oversimplify this to make you think that these are just simple machines. They are absolutely incredible devices that are made to take snapshots. They're made to be triggered when there's a head-on collision, which happens every now and then, several billion times a second. And they're meant to be triggered and take a snapshot of what happens in the collision. Those snapshots of proton-proton collisions are what particle physicists call data. This is what they look like. This is the cover slide I had. It is a picture of beauty, it is a picture of awe, and it is a picture of catastrophe. Really fundamental forces coming into contact, coming into close interaction, particles being ripped and thrown into the different parts of the detector. And you see those tracks emanating as electrical signals are pieced together and the snapshot is developed. So this again was not taken with an iPhone, it was taken with this machine. This is the traffic camera that I want to talk about. This is the one that I work with, that the Simon Fraser University has collaborated with. It is 44 meters long and 25 meters tall. And I would like you to try and find the human beings in this picture. I managed to find 3 of them. And they give you a sense of scale. Honestly, when you see this thing, it is just, it's awe-inspiring. It's so massive. And it is absolutely dense. It's absolutely electrified with different sensors and cables and readout to the extent that your head will just swim. So we have just talked about some really big ideas. So a really big machine, a really big detector, and maybe your head is already swimming now. You might be asking yourself, why in the world? I mean, this is really cool. Smashing protons sounds like fun, but why are physicists doing this? Why am I here? Oh, and before we get to that question, I forgot about this slide. This is a really nice overview of what I just mentioned, so we'll come back to that in a second. Here you see a proton and the proton's friend making their way through the various pre-accelerators, which are getting them up to speed for injection into this racetrack. So they are now making their way into this SPS, and now they're in the LHC, traveling at nearly the speed of light in opposite directions. So now take a peek inside the beam tube. This is now how it looks like, under 100 meters under the ground. We have our friend, the proton, with 3 quarks dancing around, minding its own business as it goes about its daily commute, entering the intersection where the Atlas detector lives, and it finds another proton minding its own business, and splat. This is really an amazing shot, showing the complexity of the device, the Atlas detector, with the various sensors, showing you the 3D trajectories that were pieced together, again, using this high-tech camera, this instrument. All right, now let's get back to the question of why the heck we do this stuff. What can we learn from this mess? And the answer is a lot. We can learn the secrets of how the universe works at the fundamental scale. To help you appreciate that, I need to explain that particle physicists have a theory. Again, the names are just the best here. So this is like a really important theory. This is one of the best theories we've ever constructed, and it's so accurate, but it's called the Standard Model. So, anyways, don't be afraid of this equation. I don't want you to be afraid of it. We're not going to walk through it. I want to show it especially for the high school students though, because I want you to realize that the laws of physics, that the work that physicists do, especially theoretical physicists, is done in a language almost like a programming language. It is the language of mathematics, right? If nature was a computer, you might say that mathematics was the programming language. And so to me, I mean, that blows me away. That is why I do physics. That is just an amazing thought. But we will be looking at the Reader's Digest version. This is kind of the consequence of the mathematics. And it consists of a table of 17 different boxes. Okay? They contain the building blocks of the universe. And it's almost like the periodic table, isn't it? Except it's way better, because it embodies the symmetries, the patterns of that equation, of this equation here. So it's just filled with all sorts of beautiful relationships. And we'll start digging into it right now. The first generation here is what we call the first column. And it contains some familiar faces, right? We have the electron at the top, the up quark, and the down quark. And now the electron has decided to bring along her friend, this one here. So we need to talk about this fourth particle. It does not make up atoms. It is called the electron neutrino with the Greek symbol nu. It's a very sneaky particle, okay? And it is a friend to the electron, just like the down quark is a friend to the up quark. Okay, mathematically, that is a relationship. And whether or not you care about this particle, it is constantly bombarding your body. It is constantly making this flux of this particle coming from the sun, where they are produced in copious quantities, and they're traveling through your body. They're on the order of 100 billion traveling through your fingernail every second. And you know what happens at nighttime when the Earth is between us and the sun? They don't care, these neutrinos. They just go straight through the Earth, and they continue pummeling your fingernail day and night. And we also might not care because they're so sneaky. And they don't interact with us. They're very difficult to detect. But okay, this is the first generation of matter. Neutrinos are important. Let's look at these other two columns. Why do we need the other two columns? The answer is we don't know. We know that they exist. We know the mathematics and describe them in a similar way as the first column, and they happen to be basically copies of the first generation, but with heavier masses, with more mass. As a result of their large mass, all of these particles are very unstable, and they tend to decay in a split second. Just like some of the chemical elements also are radioactive and they decay. So if they don't really influence our daily life, then why are they there? I want to stress again that there are mysteries in particle physics. Some physicists believe that there is a mathematical reason why there need to be 3 columns. There are some good empirical reasons why we believe there are no more than 3, but we don't know why there are 3. With that said, let's look at the last column here, which is a totally different type of particle. These are called force carriers. If it weren't for this column, none of these particles, none of the first 3 generations would be able to interact with each other. These forces in the language of the standard model are what enable interactions between the first 3 generations. The most familiar one is up here. It's symbolized by the Greek letter gamma. Does anyone know what this particle is? The photon. So this is a particle of light, as you might think of it. It mediates, or it represents, the electromagnetic force. When I tell you these things, in the back of my mind, I'm thinking of the mathematics, but we need to think of a way to explain this to you. And the best way to get a hold on this is to think that the photon communicates the force of electromagnetism. Similarly, this G, the gluon we just mentioned, it mediates the force of the strong force, right? That was those springs that you saw in between the quarks. So these particles are very important. What are the last 2 ones here? These particles are just pretty wild. So these 2 ones here together represent a third force of nature called the weak force. And I don't have time to dig into them, but they are very interesting particles. Let's take a look at what I mean when I say this particle mediates that force. Here is the physicist's equivalent of a stick figure. They really like drawing these things. If you've ever watched Big Bang Theory, you might see these kind of on the whiteboards or whatever. But really there is an intuition that you can gain from these diagrams. You see time moving from the left to the right. You see you start with two electrons and they approach each other, and at some point, what? They feel each other. They can sense the presence of the other electron, and we know that. That's electrical repulsion. You bring two electrons close to each other and they push away. How is that described mathematically? In this diagram, you can see what happens is they establish a line of communication, this photon, through which they communicate to each other, in a sense. They share their momentum through that line. So literally, this electron said, I will give you some of my momentum, you give me some of your momentum, and we end up traveling away in time with rearranged kinematics, right? The kinematics is redistributed. And in the case of repulsion, they end up shooting back outwards. This is what we mean mathematically. Another example, this is something that could happen when two protons collide. Now, you might have an up quark from proton A coming into contact with a down quark from proton B, and they establish a line of communication through the strong force. Now they're not using the photon, but they're using this symbol for the gluon. And in fact, they might be attracted to each other. They might form a different particle called a pion and rip out of the two protons, and that's when the rest of the proton breaks apart and then flies into your detector, like those snapshots we saw. So this is another important example of these sorts of interactions. I need to keep moving here, but we have not talked yet about the Higgs boson. So this is perhaps particle physicists' favorite particle. It's just like the baby, you know. It's so important that it was one of the driving reasons for building the Large Hadron Collider. And long before there were any signs that it existed, in the 60s, physicists were developing theories, they were developing these mathematics I showed you, and they realized there was a problem, because if the mathematics was correct, all of the rest of the particles should have no mass. They should all be like the photon, which zips around with no mass. But that's not the case, right? Electrons, they have mass. So where does it come from? And I can't explain to you all the details, but essentially physicists hypothesized that there was a field filling all of space and time, just like you would take, you could say that the temperature of the entire universe, you could put a number at each point in space representing the temperature. In a similar way, you could put a number in every point in space and time representing the value of this Higgs field. And it was through interacting with that Higgs field that particles attain the property we call mass. Some of them interact more strongly with the Higgs field, and that gives them more mass. Some of them don't really interact at all, just a little bit, and maybe they get a tiny mass. So they were, the physicists, this sounds really silly, all of this, doesn't it? But the physicists were so convinced by the mathematics that they postulated, they expected this particle to be produced in the future. And so much so that this was a strong motivation for building the multi-billion-dollar Large Hadron Collider. It was not long after the construction was completed, in 2010, as the data started coming in from the Large Hadron Collider, that teams of students like myself, professors, postgraduate researchers started hunting for signs of this particle. They started looking through the evidence, sifting through the evidence, trying to see if it was being created at the Large Hadron Collider. And how would that look like? Maybe something like this. This is a little more complicated, and the fact is you can draw an infinite number of these types of diagrams, but you have to follow a few rules according to the math. And in this case, you might also be looking at something produced when a gluon from each of the protons, gluon from proton A, a gluon from proton B, come into close contact, and they can connect with each other using this little triangle, which is quite cute. It's made out of little quarks kind of going in a loop-de-loop. And the point of this diagram is not that you understand the whole thing, but just see that there is a dashed line in the middle where a Higgs boson gets created. This is one of the ways you can make it, but the problem with the Higgs boson is it doesn't stick around. It doesn't live very long at all. It lives something like 10 to the negative 22 seconds. So there's no way we can study it in this way. However, we can infer its creation by looking at what it produces. In this case, the end product is 2 photons. Do you see that? 2 photons. So you have 2 gluons from the protons coming in, boom, and then you have 2 photons coming out. So it might be as simple as looking for collisions that look something like this. You see there are 2 yellow chopsticks in this picture. Those represent the photons that we're looking for, right? We wanted to look for 2 photons coming out. That means a Higgs is being created, no? Well, it's not quite that simple. Remember I said there are an infinite number of those diagrams you could draw? There are no doubt many of them you could draw using no Higgs boson that still have 2 photons coming out. Okay, so just because you saw 2 photons doesn't mean that they came from a Higgs. So how do we find out? How can we overcome this? I will attempt to use an analogy that I think will be helpful. How many of you play Pokemon Go? Anybody? Anybody? Okay, I never got on board, but it seemed to me like a blip. You know, for those of you who don't know what it is a game that came out mid-2016 or so, and for a moment it seemed like everyone was on board, everyone was playing it on the bus, whatever it was. And to me, I don't know if this is fully true, but to me it seemed like it came, it had a brief stint, and then it kind of died away, right? So let's say I was a store owner, games store owner, I sell these Pokemon cards. Right? Pokemon cards have been around since the 90s, but people don't really play cards anymore, so the sales have been steadily dropping since the 90s, right? But I want to figure out if Pokemon Go had an impact, because maybe if someone plays Pokemon Go, they'd be more likely to buy the cards. I don't know, could be. So I would make a plot like this, which shows you the number of sales as a function of the year. As the year goes on, since the 2000s, the sales have been steadily dropping, like I said. There's this general trend. But what do you think? You think Pokemon Go had an influence on the sales? Yeah? It looks pretty, this is pretty good evidence, I think. There is a very clear trend that corresponds with the timeline of Pokemon Go being introduced and kind of tapering off in a few years. And so even though, this is the analogy, even though the store owner doesn't know for every sale what influenced that sale. You don't have that knowledge. Just like with the Large Hadron Collider, for every collision, you don't know if a Higgs was involved. You can never know. But by collecting lots and lots of collisions and looking at trends, you can see there was an excess amount. There was something else contributing in a local range. Okay? In this case, in a couple of years, in the case of the Higgs boson, that range corresponds to the energy contained by the 2 photons. So if you can understand this plot, you can understand this plot, which is called the billion-dollar plot. This is the billion-dollar bump that you see here, which convinced physicists that they were indeed creating the Higgs boson. Now, instead of the number of sales, you have the number of collisions. The code word is events divided by 2 GeV, but really think of it as the number of collisions. Right here you have 6,000 in this marker, and here you have 4,000 over here. Those are the number of collisions which produce the 2 photons, and then we categorize them according to how much energy was contained in the 2 photons. And there's a local feature that is so striking that physicists claim the discovery of the Higgs boson. So that led to a very big celebration. Physicists do get emotional sometimes, and not only that, but a Nobel Prize in 2013. So something that really bothered me when I entered graduate school, I was looking at particle physics, I was kind of interested, but I thought, hey, since you found the Higgs boson, what are y'all doing at the LHC still? Didn't you find all the boxes? What's left to discover? Okay, so I thought the field was kind of now complete, right? That was the end of the story. Nothing could be further from the truth. The story of particle physics is far from complete. I told you we have a theory. I think I told you it's a very successful theory. It even predicted the Higgs boson, but it has several problems. And so the way I see the current field of particle physics, it's almost like a good old whodunit story, you know, a whodunit mystery. The characters have been introduced, there is a crime scene, there's even a narrative, there's an account that is given by someone that explains a large amount of the evidence. It seems pretty good, but there are a few things that seem a little sketchy. And so when we look at the standard model, we see very successful theory. We know that it is correct in the things that it describes, but it cannot account for all of the evidence that we have. Let me explain to you one such piece of evidence, one such puzzle, which is causing physicists to scratch their head. Puzzle of the hierarchy of the forces. Before I even dig into this, I want to say, I want to ask if anyone has noticed that we haven't talked about one of the four forces yet so far, and that is gravity. So how does gravity fit into all of this? The answer is it doesn't. We don't know how to include it along with the photon, along with the strong. Now there are theories which attempt to do that because gravity is very well described in a different theory of different theory of physics called general relativity. It is very successfully described for many, many years, thanks to Einstein. But that's a different theory. That deals with big things, you know, stars and black holes and all that stuff. But we're talking particles. How does gravity act in terms of particles? We don't really know. And whenever we try to link up the two theories, there's some infinities that blow up in the mathematics. Now, aside from the fact that gravity doesn't even exist in the standard model, there are some other indications that there's something funny going on. So let's look at the strong force. We can give it the strength of 1, that is in some sort of units, that is how you could measure its strength. As we said, it's much more powerful than the electromagnetic force, several hundred times stronger. The weak force comes in as just a pipsqueak. Look at this, it's about 1,000 times smaller than the electromagnetic. But gravity doesn't even tip the scale. Look at all these zeros. This is insane. So physicists, when they see these numbers, are thinking to themselves, is there something underlying these numbers? Are they just coincidences? Sure, they make the universe a habitable place for us. But is that just a coincidence, or is there some reason behind the choice of strengths? Maybe all four of these strengths could be included in one, all four of these forces could be included in one unified force. So all of these ideas are on the table. But it certainly suggests something more than we are currently able to explain. Another puzzle I want to talk about, and there are many puzzles, but this one is quite popular as well. The puzzle of dark matter. So dark matter is something you've probably heard about and maybe don't know what it is. And that's because you don't have to worry about that, because physicists don't know what it is either. Whenever they call something dark, they basically mean it's a thing, but we don't know what it is. We can see the effect of dark matter. We can see that there is stuff out in the universe which is interacting using the force of gravity, but we cannot see it because it doesn't interact with light. So dark matter is this thing which is supposed to be about 5 times more, there's supposed to be 5 times more dark matter in the universe than regular matter that we can see. So there's more that we don't know than we do know. And the reason I have this picture is a picture of many galaxies that are far, far away. And if you look closely, you see that there's sort of a circular shape. It's maybe hard to see on the projector, but there's some little squints of light, maybe like this one here. And it looks like the light from these galaxies is being bent. It's being distorted by something, almost like a lens. And indeed, physicists do think that you're looking through a lens of some sort. There's something in the foreground of this image, some clump of stuff, which is lensing the light from the galaxies in the background. And that clump of stuff is invisible, but we don't see it. But it is impacting the light gravitationally. So it's interacting, it's a phenomenon we call gravitational lensing, in which the force of gravity bends space-time and allows the path of light to be distorted. So really, this is probably the closest we can get to seeing dark matter. And the best explanation for dark matter, most physicists think that it is a new type of particle. There are other theories, but one very good way to explain it is to say that a new particle exists out in the universe, or a new family of particles, dark particles or something, that we've never seen on Earth, that interact very weakly so that they don't interact with light. And but if it lives in the same theory as the rest of the particles, we should be able to create it at the Large Hadron Collider. So this is very exciting for physicists. They are trying to create dark matter particles and looking for those signatures. There are ways to explain these two puzzles that I introduced using bigger mathematical theories. There are many ways. These theories are usually called beyond standard model theories. And one of the most popular is called supersymmetry. Supersymmetry is very popular, but nobody knows if it's true. It turns out that by roughly doubling the number of boxes that you have, by introducing a symmetry which links the particles we know to a family of particles we don't know, when you do that, there are several puzzles which kind of work out. Like the puzzle of dark matter kind of works out, and the puzzle of the hierarchy of the forces also can be explained through this idea. And if it's true, there will be many other particles that we need to go and find at the LHC, because look at all these new boxes. That's sure going to keep me in business in the future, looking for all these new particles. The problem is, even though there are many good reasons to suspect that supersymmetry is true, none of the other boxes have been found. So at the Large Hadron Collider, nobody knew what would happen when they turned it on. And immediately they started looking. They are still looking for these boxes, these new particles. But they haven't found any of them yet. Now they could be lurking just around the corner, but it's becoming, I don't know, it's becoming less tempting to think of this picture as being true. But again, there are many theories. We don't know which one of them are true. And that's the reason I'm stressing this, because there are a lot of young people in this room. Maybe some of you will one day become a theoretical physicist or an experimental physicist, and you'll be working on these problems. Right? There are still problems to be solved. And that's how I enter the picture as well. So I am not looking for a Higgs boson in my research. I'm looking for something new. I'm looking for something that does not fit in any of the boxes in the standard model. And the way I look for this, along with the team of physicists that I work with, about 10 of us or so, we look for collisions that produce two muons. Not two photons like we talked about earlier, but two muons. And in this case, there are many interesting things that could happen. We do the same sort of game where we measure the amount of energy that these muons have, and we plot the number of collisions producing two muons, and we look for bumps, just like they found the Higgs, right? We also look for bumps. It's the same thing. And it turns out that there are many bumps. This is the number of collisions that produce two muons plotted versus the amount of energy that was contained in those muons. Now, all of these bumps are old news. We have known about these bumps for decades. They correspond to different states. How do I explain this? They correspond to different little clusters of particles that can be produced when you collide two protons. They're called resonances. Now, this is the last one that was discovered because in order to make this bump, you need to collide protons or whatever, produce two muons that have an energy around 10 to the 2, so 100, in this case GeV, and that turns out to be a lot of energy. That's why we went to the Large Hadron Collider, because we wanted more energy. We want to keep exploring and pushing out the number of collisions which produce muons that have a very, very high energy. And this, my friends, is what I mean by the high energy frontier. This tail end of this plot does not have many collisions. There are not many collisions which produce two muons with these sorts of energies. And that is where we want to test the standard model. We want to test and see if there's anything beyond that. And the way we do that is by looking for bumps. So the question is, are there any bumps over here? Well, from this plot, you can't really tell because there's not enough statistics yet. There's not enough data. But as the data keeps rolling in, we continue looking for bumps. And if there are bumps, that would suggest, again, something new. Something is affecting the trend that we would, at that point, have no explanation for. We would have to figure out some new theory to explain where that phenomenon is coming from. So, in this way, I feel like a bit of an explorer. I mean, I don't know about you, but I find it sad, in a sense, that there are no more distant lands to be explored on this planet. Right? There are frontiers in space. There are frontiers on this Earth, but not in terms of finding new countries or new land masses. Right? That's all over. But I still find excitement to think that there is a frontier in the world of particle physics, the high energy frontier, where the universe works in a way that we might not yet understand, that we do not yet understand. And that is the high energy frontier. That's why I do what I do. And I think that we have plenty of time for questions, which is the best part.
We have lots of time for questions. Anybody wants to ask a question?
I even gave some hints for questions throughout my talk. Yes?
Could you give us a little more about the gluon? Is that particles or force?
Good question. Is the gluon a particle or is it a force? In the description that I talked about, called the standard model, this one's fine. Forces, turns out, okay, the concept of a force, of something pushing something else, is a concept which was born in very classical physics. So Newton came up with this construct of forces, right? At the level of particles, that concept doesn't really, it's not really the way these particles work. We talk about interactions. There is something that happens, and there's a rearrangement of the momenta. So that comes back to this description where a particle in this column is seen to be a representative of a force. And the real reason that this description works is because all of these boxes that I told you were particles really represent something called quantum fields. And they are objects which are outstretched in all of space, and I don't have time to talk too much, but we think of particles as being excitations in those fields, just like you could imagine a ripple on a pond surface, which is very large. These quantum fields then are the basis both for the matter in our universe and for the forces through which they interact. So the gluon represents a ripple in this quantum field of the gluon field. So, and in that way, it communicates this force. And I understand that this is probably not satisfactory for your question, but when we see a gluon inside the proton, which is holding together, which is communicating that force, it is a local excitation of a field that actually fills all of space. So that's the best I can do. These ideas are very vast and beautiful ideas. Yes?
What's so special about the two muons that you're looking for?
Good question. What's so special about the two muons you're looking for? And the answer is, there's nothing really special about them. This one, there's the picture. You see they're coming out there. Again, there are many different ways that you can make this happen. There are many different collisions which will produce two muons. And so there isn't anything special about that. But again, we want to see if something is, we we want to see if there is, so I said there are many different ways to make two muons, right? And we think we know all of the ways to make two muons. But maybe we find a new way in which to make, I won't show you that one. Maybe we find a new way to make two muons that we've never seen before. And that would cause more of these muons because there's something new. Does that kind of help?
Yeah, but what about two tau?
Okay, I see. All right. So she's talking about tau particles. All right, let's talk about, that's a good question. What are the tau? I didn't introduce the tauons. So here's the electron, here's the muon, and here's the tauon. These three particles are kind of like cousins. Okay, they share many properties. Like I said, these are kind of like copycats of the electron, but they have more mass. So there are many collisions which produce two tauons as well. There is something special about muons though. Turns out that they don't interact as much as the electron because they're so massive. And they are able to get through the whole detector. Look at that. So most of these particles are dying inside the middle, but some of them make it all the way out. And muons are very special because they do. They make it all the way out. Tauons, they are also special. They have a different property. They would make it all the way out if they lived long enough. So muons, they do live long enough to make it all the way out. Tauons, they die so quickly, they decay into something else that they never make it past this center part. So all of these particles have different properties and they're all very special particles. Okay, yes?
So I believe you said that the Higgs boson is like the field and another particle energy gives that particle mass. But like how can something that is no mass in the first place gain mass by interaction?
Very good question. The way, I didn't talk about the way in which the Higgs field attributes mass. The description, something that is called the Higgs mechanism, is a mathematical description. And I won't go into that, but one analogy that has been used, and it's not a great analogy, but we tried, right? Is that just like you saw the snow outside today, there are some particles, now you imagine three different people trying to make their way through the snow. One of them has regular shoes like me, one of them has snowshoes, and one of them has skis. Who do you think is going to be the fastest in the snow? The skier, right? And in this way, you can think that if this field is filling all of space, there are some particles which don't really feel that field. They don't really interact with it. And so they're light. And there are some particles which are very heavy particles, which interact very strongly with that field. And I think that's the best I can do. Very good question, though. And I would encourage you to not stop at that and try to get to the real picture, which is, again, in the mathematics. Yes?
So are you detecting the muons outside of the atlas?
One of the reasons the Atlas detector is so big is because we have to try and catch the muons. They escape, and so because they're so sneaky, we want to make sure that they they deposit some of their energy as they leave. And that's really all of this part outside here. A lot of that is just for the sake of detecting muons. So we catch little pieces of energy that they leave behind as they leave the detector. But we don't manage to actually capture the whole muon and stop it. Does that answer your question? Yeah? Okay. Yeah, they're slippery. Yes?
I'm curious about the capabilities of the LHC. It's been around for a while. Like at the beginning of your talk, you mentioned the notion of splitting a quark, for example. What kind of energy would that take? And is it within the capabilities of this collider, or is there something bigger on the horizon?
Okay, that's good. I see kind of two questions, which is one, would we be able to split quarks, for instance, or what would we be able to do with the Large Hadron Collider, and is there something else in the future? And I'll answer the second one, which is yes, there are colliders which are now being really envisioned, and physicists are thinking already of tomorrow's big collider. There are a few of them that they want to build, but again, funding. And so back to the Large Hadron Collider, it is scheduled to run for, yeah, I guess at least 2 more decades with several breaks. And to answer your question about quarks, well, we don't know. I mean, the thing is, we don't have a theory where quarks are built out of smaller ones. There may be some, maybe one called Technicolor, or string theory, for instance. But we wouldn't, since we don't have any measurements of the force that binds them, we don't know how much it would take. But what we can do is we can say we will try to split them as best we can, and if we don't, then we can set limits on how strong that force should be. We say, well, we couldn't split it with this amount of energy, so it obviously must be stronger than that. Okay, then we try with more energy. Okay, it's got to be stronger than that. And this is what we call setting limits on some parameter. So we don't know if it would be able to split quarks, but it is 100 times more powerful than the previous collider experiment, the Large Hadron Collider. So, yeah.
So what are your opinions on the string theory?
Good question. Well, I'm certainly no expert to speak about string theory. I did do a research project in school once where I tried to dig into string theory because I also thought it's a very fascinating thing. And again, my head kind of swam when I did that because, I don't know, I wasn't cut out to study string theory apparently. Not many people are. But it's a very beautiful picture. It is. It's a very beautiful theory in which all of the particles that I showed you derive from one, the simpler picture again, which consists of kind of bundles of energy called strings. And they come in different types, right? You can imagine having a string that is open on both ends. And then you can also have a string which is closed. And those correspond to different types of particles. And you can excite the string in different ways. And those excitation levels correspond also to different particles. The nice thing about string theory is that gravity comes in, what's it? Out of the box, or what's the word? It comes in plug and play. Gravity is there, which is one of the biggest reasons why physicists want string theory to be true. I don't know. The biggest problem with string theory at the moment is that physicists don't know how to make predictions using it. So they have not figured out yet how to connect string theory to something we can test in the lab. And so while they're still working on the theory and making it beautiful, we don't know if it's true. So yeah. Yes?
Also, for a fundamental particle like an electron, if it has a negative charge, then where does it keep the charge?
Where does it keep the charge? In its back pocket. This is a very good question. So the question is, where does the electron keep its charge? And we don't know. We don't know. These basic questions are sometimes what are needed to help physicists expand the way they think, to help physicists come up with new theories. We don't know how big the electron is. We think that it's very, very, very small, but we can't measure it. We don't know if the charge, if it's like a little ball with the charge sitting on the outside, or if it's all on the inside. We don't know. It's a very good question. Good questions. Anyone on this side? Nobody asked me about the colors that I use for the different quarks. Does somebody want to ask me? No? Okay. Yes?
Why do the quarks have like different colors?
Let's go way back. Okay, so this is a very beautiful part of the theory. Now, they don't really have different colors, but when physicists were exploring this new strong force, they found that in the mathematics required to describe this force, there was not just one charge like in a